We'll continue today with thermodynamics. At the beginning that we will start with information theory, then go into quantum thermodynamics. And my original plan was maybe to already treat quantum yesterday, but actually so far we haven't seen much quantum. But that's the topic of today. So we will see we will ask questions like what is really different if we treat things quantum mechanically, and what do quantum effects really mean? How can we treat them in a consistent way in thermodynamics? And connected to that, I will also have to, in many cases, say that we don't have an answer because, as you know, quantum thermodynamics is a current field of research. And so there are actually quite fundamental questions that one may at first sight think that they should have been answered already many years ago that are still open. But I think this makes the field actually very interesting also as a research topic for current research, because it's not just some specialized questions that are still open, it's really some very basic questions that are unanswered so far. And we don't even have the right framework to phrase them, or some of them at least. But let me start with something we have seen yesterday. So yesterday I told you about in some ways small machines, like for example the trapdoor in Maxwell's demon is in some ways a mechanism that would operate on a nanomechanical level, or on the quantum level if you want. And the same is true for Szilard's engine. So Szilard's engines was this thing where we had one particle. And you may have rightly so thought that this is maybe not a very realistic thing. And indeed Szilard proposed that as a Gedanken experiment and didn't probably have in mind to actually build it. However, today we have the technology to build devices on the level of individual particles. We are not building a Szilard engine because it's hard to put a piston and all that, but we can build devices which are essentially equivalent to a Szilard engine. Or at least, I shouldn't say we can actually build them, but at least we now have the technology which allows us, in principle, to build them. There are certain difficulties that I will discuss, but now today it's certainly the right time to think about actually what can we construct and how can we actually realize these things. So the first thing I would like to do is to present a mechanism, an explicit or more or less explicit, and it will still be on an abstract level, but a mechanism to erase one bit. And what we have seen yesterday was just a bound. Maybe I should erase. Okay, maybe I will leave that. So what we have seen yesterday is Landauer's principle. And Landauer's principle was in some way an upper bound or a lower bound on the consumed energy that applies to any mechanism that one could think of, or at least any mechanism that would be compatible with the second law of thermodynamics. So Landauer's principle said that for any mechanism, the work cost for erasing one bit is at least the Boltzmann constant times T times ln2. And so remember the Boltzmann constant is something very small, and the T is the temperature to which the mechanism of the reservoir to which the mechanism is coupled. And maybe wasn't so clear yesterday when I talked about it. So what you should think of is a mechanism of the following form. You have a bit, x, and you have a machine, an erasure machine in some way, or a gate or whatever. And the output of the gate will be some fixed state like a 0. However, clearly this is an irreversible process because independently of whether the bit is 0 or 1, you will get a 0 here. And any independent process, or any for an irreversible process, it's impossible to describe any irreversible process on a closed system. So in some way, in order to be able to even possibly describe that, with the laws of physics, which are reversible, we have to include a second system that acts like a bath. And in principle, we can choose what this system should be. But of course, we want to take a system that we actually have for free in some way. And what we have for free is a thermal reservoir. I mean, if a machine operates in some environment which has a certain temperature, and it would say, okay, let's couple this machine to the environment which has a certain temperature. So we assume implicitly that there is this thermal environment around. And now the efficiency or the work cost of the machine will depend on this temperature. And indeed, this is actually quite intuitive, because let's assume that the temperature of the environment is 0. If it was 0, a simple way to erase the bit would be to move the bit somehow into the environment and just replace it by some fresh system from the environment. And if the temperature of the environment is 0, and if we assume that there are not degenerate levels, then we could kind of take a system from the environment which is pure, somehow the ground state of some atom, and just output that as the erased bit. However, if the temperature of the environment is high, then the machine is essentially surrounded by mixed states. So this mechanism, this very simple trick of just moving that bit into the environment and replace it by something else wouldn't work. So you have to do more work. But the work would indeed go to 0 if the temperature is 0, because in that case it's very easy to actually output the pure state here. So, I mean, outputting a 0 means outputting a pure state. By the way, regarding this number, this is joule per Kelvin. Someone asked yesterday, what is the actual work consumption of the human brain? I was mentioning that, and then someone asked, what is the number there? And I looked that up this morning, and I mean, the first thing I learned is that people in biology or in neural science, they don't use joule to measure work. They use how many molecules, energy molecules are used. So they have these ATP molecules, the adenosine triphosphate molecules, and they just ask themselves how many ATP molecules are consumed, for example, to transmit 1 bit. This is the type of answers they give. And there are many papers about that, where experimental papers and theoretical papers. The experimental ones are mostly on rats, apparently. And they found that the transmission, I mean, they looked at transmission of a bit. This is not exactly erasure, but it probably gives a kind of an impression of what kind of the processing of 1 bit costs, at least the order of magnitude. And what they found, maybe I write this here just as a comparison briefly to answer this question. So the brain would roughly consume 10 to the minus 15. So I converted that in joule, joules per bit. So this bit really refers to a communication. So in principle, I could argue a communication is, of course, even actually a reversible operation. It's not an erasure, but it's in some way corresponds to a neuron firing, and then so this kind of creates a bit and in some way also erases it. So this can now be compared to this number. So if we multiply that with the temperature, we get something of the order of 10 to the minus 20 or 10 to the minus 21. So we are essentially away by a factor of 10 to the 6 to 10 to the, or maybe if you are generous, 10 to the 5 to 10 to the 8. So the brain could energy-wise be 10 to the 5 times more efficient. However, I mean, that's just the limit. So no one would claim that this is actually would indeed be possible, because the brain, of course, operates in a noisy environment, and in some way what is relevant, and this is also discussed in these papers that I found, is the signal-to-noise ratio. So in some way it's much harder to generate a bit in a wire which has noise, because then what you actually do is you generate the bit redundantly. So in some way you could think of it that with that energy consumption you could generate 10 to the 5 copies of the bit, and this makes it kind of error tolerant. Anyway, this is just a short side about the human brain, but let's now look at the mechanism which comes actually close to that bound. And this mechanism that I describe is actually pretty standard now in the literature. So it's kind of also described on a generic level, but it gives you at least an impression of how people think about these things. So how can one erase a bit? And so as I said, I will still do that on a relatively abstract level, but so I will just assume that I have a two-level or a system that has two states. And when you are actually in your PhD working on systems, you could now take any system of your choice, so an ion or whatever, a quantum dot, and you identify two particular states, but you assume that you can do the following. So the two states should be degenerate, so there's some energy E0, but you should be able to somehow, by applying, for example, external fields, raise one of the energy levels. So the idea is, so the assumptions are that it is possible to raise and lower the energy levels. And now there is one part of this assumption which is, at least I would say for today's experiment, at least challenging, if not probably impossible. But I will later tell you how one could circumvent that. But let's for the moment assume that if the level is occupied and lowered or raised by some amount delta E, then one gains or has to invest if one raises it. Delta E work. So in other words, one shouldn't be wasteful, and let's say if this is driven by an electromagnetic field, increasing this field should only cost you as much work as is required to, as is given by this energy difference. So if I have here an energy E1, let's say, and I raise this to E1, so maybe I should draw it like that. So I go from, if I go from this situation where this one is occupied to this situation here, then the assumption is that the work cost of that is just delta E, where delta E is this difference here. So that would require you to have a very precise control of your fields and so on. And probably is almost unrealistic if you think of the field as something classical. But as I said, we will circumvent that later. So let's just for the moment work with this assumption that we can do that. And in the same way, if we lower that, we actually can somehow draw the energy from the system and put it into a battery. That's the assumption. Then the other assumption is that we can isolate or couple, depending on what we want, and we can do both, the system to a thermal bath at a given temperature, which I call T. So that's something that is, on the other hand, rather easy. I just wait until the system, I couple it, and then the specific assumption is then I get a distribution which has the following form. So if I have a system which has now two energy levels, E0 and E1, then I get something that has just a Gibbs distribution. So in other words, the occupation probability, so the probability of occupation, so this probability is defined by that I would measure where is my particle, and then the probability by which I see it at E0 would be given by e to the minus beta E0 divided by e to the minus beta E0 plus e to the minus beta E1. And the same for P1. And so, and beta is here just the inverse temperature. So that's essentially the Gibbs distribution that I wrote down here. But this will be important for the calculations to use that. So beta is 1 over kb times the temperature of the bath. So these are the assumptions. And the idea is now that based on these assumptions, so this is now kind of a model system, the idea is now to use these elements in the right way and construct a scheme which erases a bit. So in some way, it's like constructing an algorithm, a very simple one. You have some basic elements like the gates or the individual steps, and now you have to compose them in a clever way in order to get a certain task done. And the task you want to have done is to erase a bit. So what does it mean to erase a bit? We first need to somehow encode the bit. So the idea is that the encoding of the bit is the following. So if we just encode the bit value into which state we have. So the bit 0 would be that this thing is occupied and this is empty, and the bit 1 would mean that this is empty and this one is occupied. And I will also draw a circle which is not filled if I don't know where the bit is. So this will just be for later in order to maybe I have to clean the whole thing in that case. So the idea is that an unknown bit will be depicted like that. So here this just means that bit is unknown. So I don't know which of the levels is occupied. Now maybe some of you have some idea of how one could achieve that task. So the question is, how can I use these steps to erase that bit? So I would kind of start with that situation. I can now lower and raise energy levels. I can connect things to a bath. And at the end, I want to end up here. I want to achieve this situation here. Are there any ideas of how one could do that? Yes, you have. Oh, sorry. Yes, you had.
Put E1 really high, so it's much higher than the thermal occupation level. Couple it to the heat bath, such it would decay there. Switch off the coupling and put it back to E0.
Okay. You had a similar suggestion? Okay. So luckily I don't have to make an account of that, but ETH has in this case one. Let's follow this idea. So this is indeed the right idea. So you have the proposal is indeed to use the fact that if you raise an energy level, it's much more unlikely to be occupied. That's essentially what this formula here tells us. So the scheme that has been proposed is the following. It's actually very simple. So we start, as I said, with an unknown bit. And now the first thing we do is to couple it to the reservoir. So couple to reservoir. This is something I can do. So what happens in this case is that, I mean, here I don't actually know how the distribution is. It could be in principle that the bit value is 0 or it's certainly 1. And after I couple it, I will be sure it will be essentially here or here with equal probability. That's what this formula tells me, because in that case E0 is equal to E1. So there's not much going on in this step. But now I keep it coupled. So maybe I draw that here. I indicate that here. This would be the heat reservoir. Now the next step is to actually raise the energy level, so of one of the two things. So here I raise this. So I go up here. And so what will happen, maybe I can indicate that like that, the probability that the particle is here will now become larger. And this is because while I raise this, I keep the coupling to the bath. And because I keep the coupling to the bath, I will, at any time, let's assume I do that slowly, so that this formula applies, I will at any time have a probability distribution that is given by that. And you see the higher E1 is, the smaller is this probability to find the particle there. So P1 here is now will become much smaller than P0. And I could actually do that in a limit. So let's assume I raise that up to infinity. Of course, in practice, I could just go very high. And that would be sufficient because it's exponential. Now, the next step is to isolate the system again. So isolate it from the bath. And now finally I lower the level. So what I do now is I go back with the energy level. But it's clear that because I go back while the system is isolated, this level here will not fill. So I end up, or maybe I should indicate that like that. At the end I'm down with this level, and I know the particle is certainly here. So that's essentially the process. So what I have done is now I started from this unknown bit, and I have reached a situation where the bit is certainly a bit value 0. So it's a very simple process in that sense. Now, how would you calculate how much work was done or used in this process? I mean, Landauer already tells us that, I mean, you saw the formula on the back of this blackboard, that there is a certain minimum work cost. So where is this work invested? Which of these steps consumes work? Any ideas? You have that?
Well, when you raise the energy while the particle is still in the elevated state.
Yes, right. So this is kind of the step when we raise this thing, because there is a certain probability that the particle is here, and we raise it. And because there's a probability that the particle is here, and here we assumed that if the particle is there, this costs that amount of work, we have to take that into account. Is there any other step which costs work? Yes?
So if a particle is not there and we lower the level, we don't get the energy back.
So we
don't get the work back from the system if we lower the state.
Here we don't get the work back. No, that's right. Because I mean, this doesn't cost work, but we also don't get anything back because the level is empty. And okay, maybe I should have written that here said if it's occupied, then it costs that amount of work. I should also maybe have written that if it isn't, then I can do it for free because there's nothing there. So I essentially change the energy of something that is empty. So I don't actually change the energy of the system at all. I mean, that's an assumption, and that's hard in practice as well. But let's assume this is the case. So under these assumptions, indeed, this is the only step where that costs energy, because coupling it to a bath just means to bring it close to a bath. Of course, in practice, that would also have certain energy costs, but this can be made arbitrarily slow, and in principle, with arbitrary little energy consumption. But here I have a fundamental energy consumption, which is given by the fact that I really raise the energy of the system. And here again, isolating is like coupling it, and here lowering, as I said, here we have the assumption it's not consuming any energy. So what is left to do is just to calculate here how much energy we invested into this process here. So let me briefly calculate that. So it's actually quite a simple calculation, but let me nevertheless do it, because it's kind of instructive to see. It's kind of very similar to the Szilard engine when you do that. And so you will see that hopefully that all these processes, or you get at least an intuition that all these processes must consume roughly the same amount of work. So the one way to calculate it is to do it in infinitesimal steps. So I would say, let's just consider the process of raising the energy level. I start essentially from the energy level. I mean, let's assume for simplicity that E0 is 0 and E1 is just E, or is E, okay, let's keep that, is E1, but this E1 goes then to infinity. So I start here from 0, and I write it like that. And now I have, in each infinitesimal step, I raise the energy by delta E. Now this would be the work consumption if it was certainly occupied. So it would be infinite. But now the assumption that we made is that at any point in time, the probability that the particle has this particular energy is given by this Gibbs distribution. So I write here the probability that the particle is in this distribution, and this is given by e to the minus beta e divided by 1 plus e to the minus beta e. So the implicit assumption here, which I now should make explicit, is that this process is done very slowly, so that in each time step, in each of these infinitesimal time steps, there is again new thermalization, so there are no correlations. So it's not that if the particle was before in E1, it will stay there in the next time step. So I do the step, and then I wait until it has again thermalized, so that this probabilistic expression applies in each of the steps separately. So that just means be arbitrarily slow. And if you do it faster, then you have to take into account certain correction terms. Now this is a very easy integral to solve. So essentially, it gives you log, or actually I have to take into account the constant, minus 1 over beta times log, or ln, not log, ln of 1 plus e to the minus beta e, evaluated at 0 and infinity. I mean, to verify that, just take the derivative of that with e, and you will see that, because if you take the derivative, then you get, because of the logarithm, 1 over that, and then the inner derivative gives you this e to the minus beta e, and the prefactor comes from the derivative of this exponent here. This cancels with that. So you get this. So if I evaluate that, then clearly the term where e is infinity disappears, because here I have just e to the minus infinity, this gives 0, and the logarithm of 1 is 0. So the only term that is left is the one where e is 0, in which case this thing here in the bracket is 2. So I get 1 over beta times ln 2, which is kb t ln 2. So what do we conclude from that? Any ideas? What does this formula tell us? It's a pretty good mechanism, yes. Why are you only saying pretty good?
So you reached the Landauer.
Yes, so it's actually a very good mechanism, if it worked like that. Because this is exactly the Landauer limit. So I have done it at the theoretical limit. If I could do it better, I would actually break the second law. You had some question?
I think finite one is not true. We have always probability left that Q is not being reset.
Okay, you're saying there's always a small probability that it's not reset. This is correct. So I made several idealizations here. One is that I can raise it to infinity. So what the statement is essentially, if one wants to phrase it more mathematically, that however close you would want to come to that, there is a mechanism which achieves that. And then it's precise statement. So the precise statement is indeed that within this model, of course one can dispute about the model and or discuss the model and say the model is not realistic. But within the model, the claim is that you can come arbitrarily close to that. And so in that sense, it's a pretty strong claim. Yes?
And I don't completely sure, but if these temperatures are different for the... I remember you said that...
Yes, I will come to that. This will be my next thing. So what happens if the temperatures are different? And what are the questions to that process itself? And this is a very generic erasure process in some way. And as I said, the big disadvantage of this description is that there is this vague thing about saying that if I raise an energy level, this costs me only that amount of work, and if I lower it, I gain that amount of work. And if it's empty, this doesn't even cost anything. So this is somehow a little bit problematic, because it's in some way, I call that a half-classical description. So I'm actually talking about the quantum system, but I'm also implicitly talking about the classical mechanism which would allow me to raise and lower energy levels. So I'm kind of not describing everything in the same picture. And we will actually, in 10 minutes or so, come back to that and do it in a cleaner way, where everything is quantum, including the kind of work system. So now the kind of external system, the battery that gets the work, is kind of hidden. It's just the thing that raises and lowers the energy levels. Yes?
Could you explain a little bit again? It was a little bit lost. So because we have assumed that the level is occupied, we perform the work to raise it. And during this procedure, the level is all the time occupied because we're still raising it. And then suddenly, when we get to the top, the probability drops to zero. So suddenly, this level is no longer.
Okay, this is a good point. So one has to be very careful in these infinitesimal steps. So the idea is the following. In some way, implicitly, I used something like the law of large numbers, because what I said is that let's just describe the process with very small steps, and the steps are chosen. So you could imagine a process in which I do a small step, and then I wait for a long time, then I do very fast again another step. So this means that during the time I do the step, the particle stays in that position. So I start here, maybe the particle is actually here. Now I do a first step and raise this a little bit, and the assumption is that I do that fast, that step. But then I wait for a long time. So now I wait. No, that's not what. Where put in? So, I mean, this is indeed something one has to analyze more carefully if one really wants to make a mathematically precise statement. But let me just give you the intuition. So I would stay here, and so this would be fast. So fast means essentially adiabatic in some way. So I'm just doing that, and then I wait. So I thermalize. So this is kind of thermal. So this is now lowered, and now I get a new sample, so to speak. So now it could happen probabilistically that the particle is now here. So now if I do the step again, so now I do again the fast step where I raise this again, this didn't cost me any energy. And so on. So I continue with that. And now what I'm essentially doing is to calculate the average work used. So the average work is now given by this distribution. Now you could ask, is the average work corresponding to the actual work I'm using? And however, if I make these steps, if I decompose that into infinitely many steps, or a very large number of steps, the deviation of the mean, of the average from the actual thing will just scale with the square root of the number of steps, or 1 over the square root of the number of steps. So if I make the steps very large, the law of large numbers essentially guarantees that this average energy consumption that I calculated here will correspond to the actual energy consumption of one individual process like that. So somehow I'm average. So in each step, it's kind of probabilistically either consuming energy or not. But because there are many kind of probabilistic samples I take, infinitely many, if I decompose it into arbitrarily many steps, then this average that I compute will correspond to what I actually have in the specific process.
Then couldn't we say that when we lower it, the same way the probability grows? So
no, there's a big difference between the raising and lowering. So while I raise, I'm coupled to the thermal bath. Whereas while I'm lowering it, I keep the system completely isolated. So that's the difference. It's like, in some way, if you think about the Carnot cycle, we have an adiabatic part and an isothermal part. And so in one, it's assumed it's coupled to the thermal bath, and in the other not. And this gives a very different behavior. Yes. Are there other questions regarding this process? If not, I would maybe now come to this question that was now asked, even on, I think you asked this question as well on Monday, about the different temperatures. And this actually will give us a heat engine, as you can probably already guess. So the idea is, let's now assume that we have this mechanism given as a box. So someone constructed that. Now can use that to generate much more interesting systems. For example, this is already sufficient to build a fridge. So if you need a fridge and you have this little device to erase a bit, then you can just use that. So how does this work? So what is a fridge? A fridge is a machine which is kind of coupled to a cold reservoir. So we have something TC, so this is cold. Or, okay, sorry, I should maybe start with the hot one. This is easier. So this is the hot one, and then I have a T cold. This is a cold one, and then I have a battery, so to speak. But the battery will now be more or less irrelevant, or we don't have to put it explicitly. It's relevant, but it doesn't have to be explicit. Now, what is the idea? I somehow start with, okay, I could now do two things, depending on in which direction I want to run it. Maybe let me first, before I do the fridge, do a thermal machine. So I want to use the temperature difference between these two reservoirs in order to draw usable work. So I want to charge this battery using the temperature difference. So how do I do that? Let's assume we have a bit 0 given. Now, what I can do here is to kind of run the process, that I have to explain, of the erasure process in reverse. I call that randomize, or maybe I could call it erase to the -1. So I run the erasure process in reverse. I mean, I will just describe what that means, but what it essentially will give us is some bit which is no longer erased. It has some value which is unknown. Now I feed that into an erasure process which is coupled to that reservoir here. And then I have again a bit 0. And then I just feed that 0 bit again here in. So I have a cyclic process. Of course, these machines here have to be driven by something. So I have to connect these machines to the battery. So here we have the battery, and here as well. But this is essentially the idea of the heat engine. So what do I mean by this erasure? The erasure is already clear, but what do I mean by the randomizer process? The randomizer process is just based on the observation that if I drew the same thing that I drew before, and maybe I should do that in the opposite order, then I actually get a mechanism that randomizes a bit, but extracts work from it. So I have this, I raise this up to infinity, then I couple to reservoir. So when I couple to reservoir, this stays at infinity. And now I lower the level of E1. So here I raised it, I lower it. While I'm lowering it, it's coupled to the thermal reservoir. And so what I get at the end is kind of an equal distribution of that. So I have somehow a random bit. Now, obviously, this process of lowering it from here to here is exactly the opposite of the process of going from here to here. So I can do the same integration I did before. And what I find is, of course, that I can exactly extract that amount of work. So if I have a machine to erase a bit, if I run it in reverse, I can essentially use that machine for the following purpose. I feed the machine with a bit 0, and the machine will output here a random bit x, but it will also output energy that I can use to charge my battery, and exactly this amount here. So this is kind of nice. This is really this idea that I mentioned of Charlie Bennett, who wants to drive cars using a memory stick. So this would be the 0 bit of the memory stick. So this is the memory stick you feed into the car. It's, I think, an idea that in principle works, and it's kind of nice to think about it. And then you drive your car, you get this thing, and at the end of the day you have this memory stick filled with random bits. And the idea of this is now to use that process, but then you erase the random bits again in a colder reservoir. Now the calculation is very easy. So if you run this once, what is the work consumed, or the work we get in this process? So the work is given by the work required to randomize, or the work obtained by randomizing minus the work needed to erase it again. Now I just have to put in the formula. So this is KB ln2 times T. So the randomization is done with the hot reservoir minus T cold reservoir. So I have a very simple formula for the work I gain in one cycle of this process. So if I run this once through, I charge my battery by this amount. So I first charge it a little bit more, but then I have to erase it again to put it back into the original position.
Excuse me?
Yes?
Why is it necessary to raise the energy level here? Because if you're coupled to the bath, shouldn't
You mean in this thing here?
In the randomized process.
Aha. So here it's not yet coupled. So I couple only later. So here the bath is not here. This is only here. So I need to raise it so that I can later lower it while I'm coupled to the bath. So what I want to do is I want to be very high when I couple it to the bath so I can lower it and draw the energy from the bath. So if I would raise it only here after I'm coupled, then the raising process would cost me energy because it's already filled. So I kind of
heat out of it, I understand.
Yeah.
But are we able to randomize the bit without raising the energy level in the first place?
Whether we are able to randomize the bit. Yes, I mean, what we could do is, if we just are interested in the random bit, we would just couple this system to the reservoir and we would get our randomized bit. So this is maybe funny because in the lecture of Stephanie this morning, randomness was probably seen as something expensive as a resource. In thermodynamics, so if you count, I mean, it's always the question of what you count. And in thermodynamics, you count the work to achieve something. And here, randomness is something that is really waste. So here, purity is what you want in some way. So purity has a certain work value. And if you change a pure qubit into a mixed one, or a known value into a random one, you gain work. So it's really the opposite of how we usually think in cryptography. But this is not a contradiction. It's just that we are interested in a different thing. Here we're interested in work, whereas in cryptography we don't care how much work we invest in all these processes. Okay, so now clearly I can run this process also again in the opposite way. So I could just use this as, randomize here and then erase again here, and this would then of course cost work because now everything turns around, but I would at the same time move energy from this system to that system. So I would actually cool that system down, and this means I have built a fridge. So I have a very nice fridge that is based on an information erasure, respectively, an information randomization. So that's kind of a nice way, maybe an unconventional way to understand heat engines. But indeed, this process is equivalent to a Carnot process. You can actually see that from the efficiency. So the efficiency of that process. So what does the efficiency mean? The efficiency is essentially the work I get out minus the heat that that comes from the hot reservoir. So the heat that comes from the hot reservoir is, of course, just, again, given by Kb ln2 times the temperature, because that's, the heat I get from the reservoir is equivalent to the work. So you can see that here. So when I calculate the heat, when I calculate the work needed or the work delivered by this process, then because of energy conservation, the work delivered is equivalent to the heat drawn from the reservoir. So in other words, what I get here is Kb ln2 times T hot minus T cold divided by Kb ln2 times T hot. So in other words, I get the usual thing. I can simplify that, and I get T cold minus T hot. And this you probably remember from any thermodynamics course is exactly the efficiency of the Carnot engine. So randomizing a bit and erasing it again at a different temperature is exactly what happens when you consider a usual Carnot cycle. It's just done in a technically different way, but it's absolutely equivalent. So you could even say, if you want to somehow build thermodynamics on information theory, you could say, you could even use that to define temperature. Because maybe you also remember from your thermodynamics course that temperature is actually defined as this ratio that we have here if you have an optimal machine. So you don't start with the assumption on temperature. You say, let's assume you have a reversible machine. So you convince yourself it's reversible. And then you say that by definition, temperatures have to be such that this formula characterizes their efficiency. Yes?
They're considered systems, well, there are systems which are considered to have negative temperatures. So would it still hold, or?
That's an interesting question. So in some way, if you had negative temperatures, you would, in this case, kind of violate the second law. But the point is that the negative temperature is usually a non-equilibrium system. So it would cost you work to actually maintain this negative temperature. So therefore, this would again compensate for. So if you would just plug it in by assumption and say, let's assume we have a negative temperature, then we can violate the thermodynamic laws. But of course, you need another system to create this negative temperature and maintain it. And that would kind of, again, reconcile everything with the laws of thermodynamics. So in some way, the negative temperature is more a concept that allows you to deal with non-equilibrium systems in some way. And so then you should never forget that to maintain the non-equilibrium is kind of work-intensive. Whereas here, I assume that this is something that can be is maintained by itself. So I don't need to invest any work to keep that hot. Of course, in practice, this would be a separate consideration. I have something that would keep it. But for the calculation here, I don't take that into account. This is just a hot reservoir, and the assumption is this is what is given, and I'm doing thermodynamics based on these assumptions. And if I have, for example, only one reservoir, which is usually the case, I mean, in the thermal environment, which is kind of equilibrated, then I have no way to extract heat. That's to extract work. Yes?
Referring to my question, actually it was a bit different question.
Okay.
When we define, for example, our erasing work which we need to perform to erase the information, we couple to the temperature. So from last lecture, we defined this temperature as something that we had this box with one particle, then we expanded it, and we got some water. That's why it's cost of information coupling to this temperature. But why do you say that this temperature is exactly the same as temperature in your bath? I'm like, from the beginning, you don't have temperature. You still have information.
So the information a priori, so this X value is not, this is just kind of a system which, as you correctly say, has no temperature a priori. So the relevant thing is not the temperature at which this doesn't even have one. The relevant thing is the temperature at which I execute this process.
This process is clear. I'm like concerning Landau.
Yes.
There is a different temperature, I think.
No, I think this is the same. So the Landau limit talks about an arbitrary mechanism. So maybe I didn't formulate it clear, but what Landau principle says is that it looks at the situation where this is an arbitrary machine. So this is some machine. The only assumption is that it satisfies the laws of thermodynamics, the second law. And the assumption is also that this machine is somehow coupled to a thermal reservoir at temperature T. So this is kind of the assumption in this setting. And now the Landau bound just says that however clever I design this machine, if the only thing the machine can do is to interact with this thermal reservoir and take the bit as input, then it will require that amount of work. So I should maybe also draw a battery that supplies work. But the claim is essentially a claim about such machines which are connected to a thermal reservoir and that. So I didn't make that explicit, that thermal reservoir sometimes, but one should always think of any machine to be coupled to a thermal reservoir. Otherwise, I can only do reversible processes. Otherwise, it's an isolated machine in some way. So the idea is that the process isn't. Indeed, if you read Landauer's paper, he usually doesn't talk about this reservoir. He just talks about the temperature of the machine. But in some way what the understanding is, you can model it as the mechanism of the machine by itself, and kind of the temperature of the machine is modeled as a separate reservoir with which the machine interacts. Then it's a bit cleaner. Of course, in practice, it's the actual temperature of your device. If you have an iPhone and it erases information, then the bath, the reservoir, is the iPhone itself. So in some way, the intuition is correct to say it's the temperature of the machine, but I think to have a clean treatment, you should think it that way. And then it's the same temperature in both cases, by definition. Okay, maybe one remark I should now make is that, I mean, there are many papers in the literature, or many papers on the web that you can find, which propose different mechanisms to achieve exactly that thing, or to at least to erase a bit. And it's actually quite interesting. It's like this old challenge to build a perpetuum perpetuum motion of the second kind, and to see what goes wrong in the different proposals. And just maybe as something you could think about. I will not answer it now. It will also not be an exercise. But if you're kind of bored and want to think about something, then think about the following idea. So this is also a standard idea of the CELAR engine, where people said, let's do the following thing. So we have a CELAR engine, but we don't. So the CELAR engine could be understood as a memory device in some way. So in some way you could say whether the particle is left or right is the memory. I mean, you would assume that the particle doesn't actually move too fast. And now you want to erase that memory, or conversely, you want to use that knowledge that it's pure and here or here in a way to extract work. But let's assume we actually don't know where it is. So we want to cheat. And now people propose the following. They said that actually it doesn't matter in which direction this thing moves, because we could put here a little wheel. And so this wheel, or maybe I draw it like that. So there are actually maybe two wheels. So, and then there is a little connection. So this is the piston. And now I have a kind of little rope that goes here, and here is another wheel, and I move up a weight. So this is some weight. Now, the idea of this construction is the following, that if, independently of where the particle is, the weight will be moved up. So in the situation that I drew, I will end up either in this situation that the particle is now here and the piston is now here, and this weight has now moved up, or vice versa. I mean, the other situation would be that it has moved to the other side. So the piston is now here, but the weight also has moved up because so at first sight, this looks like a machine that in both cases, independently of our knowledge of whether the particle is here or here, will actually move the weight up. And you could now ask yourself what is wrong with this construction. But this is just a side remark. Anyway, if there are no other questions about this particular erasure process, I would now move to something which is really fully quantum. So this was kind of something which didn't really involve quantum mechanics. I mean, it's fine that I used energy levels to move them around, but there was no quantum really. Now, as I said, the weakness of this whole thing is that we have described the energy reservoir as an implicit system. And let me now describe a proposal which makes everything explicit. So the energy storage in the battery is also modeled as an explicit system where I move something up on some energy levels, but I don't change the energy levels themselves. And this is, as far as I know, kind of the smallest, in some ways, thermodynamic machine. So the idea is that the construction will only involve 3 qubits, and you could actually, if you have a machine to do quantum computation with 3 qubits, you should in principle also be able to execute that protocol that realizes the thermal machine. So in other words, if you are working on a device that acts as a quantum computer and could, for example, do a Toffoli gate or some 3-qubit gate, then you should also, in some way, by some adaptations, be able to implement what I'm going to describe now, which would be interesting because it would be rather than a computation, be a thermodynamic task. But in some way, this is equally interesting. I mean, you could say, if you're working on quantum computation, why should you focus on executing algorithms that do computation? Why not do a protocol that does something other useful? For example, act as a fridge. And that's what we are going to do now. So the proposal is, this is now something more modern. So the proposal is by Skripčík. So here are some consonants. So actually, the reason why I feel allowed to do that is that he told me that his wife was never able, when they married, to write down the name. So this is kind of the abbreviation. But he's Polish, so I'm sure some Polish persons could tell me how these consonants work. But I have the legitimation by him to write him like that. Okay, so what did he propose? I mean, this was work by him and others, done in the group of Sandu Popescu. And maybe some of you have seen this work because it was highlighted also in Nature 2 years ago. And I think it's kind of an interesting proposal as an idea. So the idea is that we have 3 different qubits. So this is a qubit that I call H for hot. This is a qubit I call C for cold. And then there is a third qubit which I call, or this is actually not a qubit, maybe. This is an n-level system where n should be large. And this is essentially this is taking the functionality of a battery. Now, in contrast to what I said before, all energy levels will now stay fixed. So there's nothing hidden in moving energy levels. So these are fixed systems. They have fixed energy levels. And so the separation of this hot qubit, what I call hot qubit, should between the energy levels should be relatively large. And then I should have a smaller separation between the energy levels that the qubit C could have. And then the battery has some equally spaced energy levels. So they're all spaced by DEB for battery. And I have the following consistency constraint, namely that delta, the energy difference of the hot reservoir should be equal to that of the cold reservoir plus the energy difference of the battery. So this is my requirement for the system. And so the idea is that this qubit here, as the name indicates, is coupled to a thermal bath at the high temperature, and this is coupled to some thermal bath at the cold temperature, and this is isolated. So that's, of course, hard to manufacture, but in practice, I mean, people are now trying to do that, for example, based on, or in an ion trap implementation. So in that case, you would kind of simulate the bath with some coherent lasers and things like that, because you don't want to wait until it thermalizes with some unknown degrees of freedom. But anyway, so the idea is that you find some mechanism to couple that reasonably strongly to a bath, but also not too strongly so that the usual approximations of work. So and by the usual approximations, I mean that the system will again be in the Gibbs state if we wait. So that's the idea, so to speak, as before. So this assumption remains from the ones I gave before. The energy distribution of these, or the distribution of the occupation numbers will be the one given by the Gibbs distribution. So now the idea of this proposal is the following. So this is like a computation. So I could draw it as a circuit. I could say there is a qubit H, a qubit C, and another line which I call B. And let's, for the moment, to understand it, also assume that this n is 2. But in order to be useful, this n has to be large at the end. But it's useful to think of it in that way. And then there is a gate. And this gate will be a reversible gate. So there's no irreversibility hidden somewhere. And I call this gate usually the fridge gate, because what it does, it has the functionality of a fridge. So what must this gate do? And now I can use the usual language of quantum computation, or that we are using the gate model to describe what this gate is doing. So what this gate should do is, let me maybe make a table. So we have, again, H, C, and B. And let's use the convention that the upper one, or the upper level, has the labels 1, and the lower one has the label 0. So now what I want to do is to essentially do the following transition. I have, if the configuration is like that, and for the moment, let's assume I have only 2 levels here. I move that to 1, 0, 0. And conversely, I mean, this is one operation. If I have the opposite configuration, then this should be moved to the opposite, 0, 1, 1. And for any other input, so the idea is that on any other input, I have the identity. So for example, if the gates gets a 0, 0, 0, it will be mapped to 0, 0, 0. So the only non-trivial thing is that it swaps these two configurations. And this also, you see immediately that this is reversible. So you can write that down as a unitary, which just swaps these two joint states of the system. Now, one observation which is important is that because of this consistency condition here, this gate is actually energy conserving. Otherwise, it wouldn't be physical. So this thing is required to argue that this operation is actually allowed without interacting with a third system that supplies or consumes energy. Because you see, if I just raise these two things, so I get this energy, but I lower that one, losing this amount of energy. Okay, so I have a consistent description now of a physical system. Are there any questions regarding the setup? Because that's already all what they propose. Now we can just analyze it, and we'll see that it indeed acts like a fridge in the following sense. That, namely, when you now look at one application of this gate here, then it will indeed move energy from the cold reservoir to the hot one. But during that process, it will actually lower here the level by 1. I mean, this is almost obvious if you look at this thing, because what the gate does is that, you see, if the cold reservoir is in the excited state, it will move it back to the 0 state, which means it takes energy out of this cold reservoir. But of course, the hot reservoir will go from the 0 state to the 1. So this will be supplied with energy. And the battery state will be reduced by 1. So you go down by 1. So that's essentially already the idea, but one has to be a little bit more careful to see that it works, because of course there are also these thermal reservoirs and so on, but the intuition is already probably clear just from the setup of this gate. And I think the experimentally interesting question is, do you have the means, if you're working in a lab, to actually build that gate? And if you are, that would be extremely interesting, because then, as I said, you have a fridge. Or, again, you can run it in the opposite way, and you would have a Carnot cycle. And I think what makes this proposal really interesting is that there is no classical element in. I mean, there are still certain things that need to be discussed, and I will come back to that, but at least we don't lower or raise energy levels. So it's very clear that the energy goes here into that battery. So this is the battery system, and in each cycle, I, for example, lower this by 1, or if I run it in reverse, so if I apply this thing, I will raise this by 1. So by the way, if I go to n-level systems, I could just replace this thing by saying this is an n plus 1, which goes to n, and this n goes to n plus 1. That would be the more general description. Maybe I should have written that already at the beginning, but people usually want to argue here that it's just a 3-qubit machine.
Maybe you'll come back at the end to in the discussion of this setup. But I note that you're not using many of the postulates of quantum theory. So you're using the possible quantization of states.
Yes.
But there's no Hilbert space structure, and there's no coherence, there's no entanglement.
Yes.
And is that going to be intrinsic to these discussions? In other words, are those additional aspects of quantum evolution incompatible?
Yes, so that's a very good point. So actually, and this is all a discussion that I will maybe come back to later, but which is already also given in that paper that proposes that. So when you analyze that, you find that the analysis is most easy if you just neglect all coherences. So coherences are here actually generally hurting because they make the desired evolution deviate from the actual evolution. But let me maybe come back to that later, because I will also argue later that we have made another kind of simplifying step, which is not so well justified, namely that this gate can just be executed kind of in a controlled way. So we wait kind of until we have a thermalization, then we execute the gate, and then we wait again. So what would be more desirable is to replace that gate by a Hamiltonian, which would do that continuously. And then, of course, you automatically get, you now use the quantum.
Time-independent Hamiltonian?
Yes, a time-independent Hamiltonian. Then, of course, you have automatically coherences, because otherwise the system wouldn't even move in some way. But this is indeed then hitting some open questions which are unanswered. But it's true that so far the description doesn't use much of quantum theory, so it just uses the fact that, first of all, there are somehow these subsystems, and there is a unitary evolution and so on, but we have no superposition or anything of that type. So how does the analysis of that work? So maybe one useful thing to do is to just ask oneself, so if you think about this process as one where you would wait very long until the system is here thermalized, and then you would execute this gate once, and then you would again wait very long until the system thermalizes. If you think of it like that, then what you have to calculate is the probability that we are in one of these states. So maybe I write down again the relevant state, because I just erased it, but we want to kind of move this configuration into this configuration. And so the question is, what is the probability of this thing? So let's call that probability P minus, because the hot reservoir is in the lower state, and this here P plus. And so what I first do is to calculate, just after the thermalization, what these probabilities are. And that's very easy, because that's essentially just the Gibbs formula. So the probability minus is essentially, and I can also drop all proportionality factors. So everything that is in the Gibbs formula in the denominator can essentially be neglected. So I have something of that type. So it's given by, so P minus means the hot reservoir is essentially in the ground state. And let's again assume that this energy is 0, to simplify the notation. So this will just then correspond to a 1 in this formula, times the probability that this cold one is in state 1. So we'll get here a contribution of the type e to the minus delta EC divided by kBT. And then, if I wait long enough, these systems will be independent, because they're separately thermalized to their thermal baths. So I can multiply here with some probability, and here I don't know what the probability is. Let's call this Q1 and this one Q0. So I just multiply this with Q1. And then the probability of the other state is, of course, the opposite. It's e to the minus delta E hot divided by kBt times Q0. And now the idea is that in some way, if I run this process, I could first look at the situation in which the process would just do nothing, where I'm just at the kind of level where the distributions are such that nothing happens. And this is exactly the case if these two probabilities are the same. So as soon as I make one of these probabilities larger, then this means that the process will actually have an effect on the total probability distribution. So if I think of it in the following way, the system is described by a probability distribution before I apply the gate, and then I apply the gate, then I can ask, does the probability change? And of course, what I want is that this probability here is kind of larger than this one if I want to act as a fridge, or the other way around if I want to act as a thermal machine. So essentially, the question which probability is larger determines in which direction the system will move. So, so the relevant or critical point is kind of where I have P plus is equal to P minus. But this just means that I essentially get that Q1 divided by Q0 is equal to e to the, so I just divide these two equations by each other, and then I get e to the, now I have to be careful not to make a sign mistake, delta EC minus delta E hot divided by K dt, and let's now check the sign. So Q1 is here, so the EC should be without. Yes, I hope this is correct. So essentially, it tells me I have this ratio here. Oh, sorry, I made here a small mistake, which is very important. Of course, these are two different temperatures. Here I should have a TC and here a TH. So I'm not allowed to divide that by the same thing. So I should here have KB T hot and KB T cold and T hot. So now I can ask myself what happens. So of course, if I had just here a two-level system, so this was kind of now the assumption, then I'm actually interested. So if I want, let's first focus on the kind of thermal machine. So I want to extract work. So in that case, I'm interested that I raise this ladder here. I raise this ladder if Q1 is larger than Q0. So the question is, what is the condition that Q1 is larger than Q0? So I can just read that off from this exponent. What I need is that this delta E over KB is larger than EC over KBC. Or I could also think of it, let me write that. So so the condition is essentially that DEC divided by KB TC, and I can drop the KB, is larger than delta E hot divided by T hot. So this is my condition that needs to be satisfied, so that it's always a little bit more likely that the lower level is occupied than that one. And if I have infinitely many levels, this means that on average I will move up here. So I will charge my battery. If I start somewhere and the Q0 was larger, then I would slowly lower that in the process and thereby act the whole thing or work in the fridge regime. Now, of course, intuitively it's clear that if I'm very close to that limit where they are equal, then I will have the best efficiency. The thing will be very slow, but I will have the maximum efficiency. So in other words, I should ideally choose the delta EC such that I should ideally make sure that the fraction of delta EC divided by delta E hot is approximately equal to the fraction of the corresponding temperatures. And let's assume we do that. So let's assume we drive the machine infinitely slowly. Now we can again compute its efficiency. But now, I mean, as you can probably guess, the efficiency will now again be the Carnot efficiency. So let me briefly make this calculation. So the efficiency will, of course, be, because of the consistency condition, we had that the level spacing here was delta E hot minus delta E cold. So it's delta E hot, or delta E hot minus delta E cold. So the efficiency is given by delta E hot. And if you now insert this whole thing, then you will find 1 minus T cold divided by T hot. So again, we have a machine that operates exactly in the Carnot regime. So that's essentially what we have constructed. Okay, so that was now the very short analysis of the machine. There are now, as I said, many things one should discuss, and I would like to go briefly into this discussion now. So what do you think? I mean, maybe I should ask, what do you think could be a criticism that would be legitimate about this machine? So if I approached some of you who would do experimental work and they would ask you, please build this machine for me. And there are of course technical difficulties, but there are maybe also some that you would say are even more fundamental. So what would you consider as a problem? And I would ask you to do this, to build this thing. Any? And of course, it's first of all hard to build because it's as hard as building any other 3-qubit quantum gate, or at least as hard, because it's actually quite a complicated gate, although it looks easy that it just moves these two states, but this is kind of an inherent 3-qubit correlation, so to speak. So you cannot easily decompose that into two gates. Yes?
So one of the complaints would be that it's hard to couple qubits that are in different environments.
Yes, that's true. I would still consider that as a practical problem and not a fundamental one, but it's true that, I mean, we have here two different heat reservoirs at different temperatures, and at the end these qubits have to interact as well. So in some way we need to have qubits that can interact, and at the same time they are kind of coupled to different heat reservoirs. That's very hard, but one could of course mediate the interaction by something else. In principle, could even put them far apart and have some photons flying between them that actually mediate the interaction. But I agree, this is very hard. But I would say it's hard, but not a fundamental problem, because one could at least think of solutions where you would somehow have some auxiliary system that would somehow, like a photon, and these are ions, and they would somehow couple via this photon. Yes?
We did not really talk about superposition of states.
Yes, right, we didn't, but why is this a problem if we didn't talk about them?
I mean, it's quite classical if you just say the state is in state 0 and switch to state 1.
Yes. Maybe you mean the right thing, but of course, I mean, in some way I could say the reason why I didn't talk about this was just because I was assuming that I can execute this gate. And of course, during the execution of this gate, I mean, this gate will be implemented in a continuous way. Of course, I have a superposition between them because it will kind of be a rotation of this state into that state. And so I didn't mention it, but I would of course say, yes, of course, when you implement this gate, you will for a certain time have a superposition between these two states, which is fine, because I would say that. But indeed, the problem lies somehow in the implementation of this gate. Are there other maybe concerns that you have? Yes?
It might be hard to create a perfectly isolated system for a battery.
Yes, that's also hard, yes. Again, here I would say this is not a fundamental problem. I mean, the same sense as I would say we could, I believe at least we can do quantum computation in principle. And this doesn't seem harder than to build a quantum computer, in the sense that if I can build a system that is well isolated to make a computation, I should also be able to build that thing. It's essentially a harmonic oscillator that is well isolated. But it's hard, that I agree. But again, here I would say it's not fundamental. There's nothing that physically speaks against it as a principle, so to speak. Yes?
And as soon as you couple the battery to the other systems, it will not be equal space anymore.
Yes, this is also actually practically very hard to find a system with equal spacing, which at the same time is coupled. Again, I would say this is not fundamental in some way. You just have to be lucky and find a good. Yes?
If you want to execute a gate in a single step, you have to use a control pulse.
Yes.
Which involves time-dependent Hamiltonians. So some energy, some work is being swept under the rug.
Yes, that's indeed now going into the direction where I also have most of the concerns, the fundamental ones. Let me just come back to that, but maybe I should take another suggestion for a program.
Energy conservation, I mean, it's impossible to make exactly the same equality of energy difference. So you need some mechanism which will, to have energy conservation law, you need some mechanism to take some, let's say, inequality in energies.
Yeah, so you're saying if I had a practical system, maybe I'm not as lucky and fulfill this constraint that this thing is the sum of this and that.
Yes, and you need some mechanism to relax it to
Yes. Yes, that's true. Of course, I mean, it's absolutely true that I will never hit that exactly. This refers to another important question, namely the robustness. So any practical thing will slightly deviate from this model. And the question is, how robust is this process? And can I kind of error correct it, or can I make it fault tolerant? Like in a quantum computation, I have exactly the same problem, that my unitary that I implement will not exactly match the theory. But there we have the techniques of fault tolerance that allows us to still achieve that. So this raises the question whether there is kind of a fault tolerance mechanism which allows us to take imperfect systems and maybe build out of these imperfect systems a maybe larger system that is therefore perfect. That is indeed another fundamental question that one could ask. Let me now come back to what was said before, namely that I need control pulses to do this. So I need that in particular for the following reason. So I said that what we are doing is essentially executing a gate and then waiting again, and then again executing a gate. So the problem that you have is the following, that from what you need to have at least intuitively is the following. So you have here the timeline, and in some way, let's assume that you could just switch on a Hamiltonian, which has the property that if it runs long enough, it will exactly do the operation of the gate. So I would here kind of have, so either this Hamiltonian that would have the property that e to the minus I sum delta t times this Hamiltonian would somehow correspond to this unitary of the Fritsch gate. But of course, I always have to wait until the system thermalizes. So I would need to, and this would be the zero, the trivial Hamiltonian. So I need some control impulse which turns on the Hamiltonian, keeps it on for a time delta t, then turns it off, waits until the system thermalizes, does it again, and so on. Of course, that's just true for this particular mechanism. I'm not claiming that this is now a result that says that there's no other mechanism doing that. But at least if I implement this particular proposal, I need some control of that type. And now, as you correctly said, I mean, to implement the control mechanism, I should at least ask myself whether there is some hidden cost. And you should now be very alert to that in some way after yesterday's lecture, because you know that even erasing a bit, which seems to be the most trivial operation, costs actually quite a large amount of work if you are in this regime of single of the Boltzmann constant. And so the question that arises is indeed, is there a machine that creates such pulses, even, let's say the control machine, in a way which doesn't consume, so if we consume something of the order kBt ln2, then we are already gotten, because that's essentially the most that this whole process will extract in one cycle. So we need to have a control mechanism which consumes substantially less work than this thing. But this is already the work I need to erase a bit. And I told you yesterday that there's a more general result. So Landauer's principle says that any irreversible process somehow has this work consumption. So now I'm not aware of any way to create such a control pulse without irreversible processes that would somehow say, now it's on, and now I have a bit where I know it's on, and I need to decide or look at a watch or a clock and see how I turn it off. So I need to measure the clock, but measuring the clock will create some bits which I have to erase again and so on. So it seems to be very hard to actually find a way to even construct any machine that outputs such a signal in a way that doesn't consume any work, that is completely reversible. So in some way, just in the very innocently sounding thing that I said, let's just implement this unitary, which is usually unproblematic if you think about quantum computation, because you don't think about thermodynamic costs. I already make a lot of assumptions, so there's hidden a lot of stuff just in this statement that let's execute the unitary. So what people are now doing, and this is now, so there's no answer to that. This is now an open question, and I just discussed it very recently at a similar school with John Preskill, and he said for him this is one of the really important fundamental questions, whether there is an inherent limitation to this to any mechanism that would kind of drive a unitary or measure time, because driving a unitary and stop it means that you somehow measure time. And so the question is there a thermodynamic cost to time measurements? Something like the Landauer principle. So in other words, the research question is there kind of a Landauer type principle for time measurements or for driving unitaries in a precise way? Of course, you may think of ways to circumvent that totally and say, let's just assume that we have a Hamiltonian which we can just keep turned on and then see how this evolves. And maybe there's a clever choice of a Hamiltonian which is time independent, so you don't need control pulses, which will achieve the same task. And there is indeed there are suggestions in this direction, although they are not working so far, or they haven't been analyzed completely. Yes?
Can you just replace the qubits and the harmonic oscillator by a bunch of flying photon states, say a Fock state and two polarization states, and just fed them in long wire, neglecting losses you would have to cyclic?
Yes.
I mean, but you have to get it in the wire somehow.
Yes. I mean, so as I said, this is an open question. So maybe this works. One would have to analyze the details. So there is so far also no result that tells us this is not possible. I'm just saying this is an open question. And if you have a suggestion, it's maybe worth looking at it. So we are now at the stage of my lecture, which now comes to the end, where we are touching open questions. So this is indeed an open question. And in general, it's an open question how quantum effects here influence that. But the analysis seems in this case to just become harder if we take into account the quantum effects. Because if you look at it classically, we would probably describe that as a discrete evolution from here to here and not care about the details and just assume everything is discrete. But of course, we are not living in a world which has discrete time steps. Okay, so this was an example of something which touches open research questions, but where quantum mechanics hurts. And let me, the last 2 minutes, just mention something where quantum mechanics actually helps. And this is, again, related to that. So there we have an inherent quantum effect which gives us something which is completely impossible in a classical consideration. So I told you about Landauer's principle. But Landauer's principle was kind of limited. And because it's kind of a very classical principle. And now luckily I have learned today in the lecture of Stefanie Wehner that for a general treatment of information, it's always necessary to take into account that we may also have quantum side information. So this means that if I have a system, let's say a bit, this is a system. It could even be a classical bit. I should, for example, if I do cryptography, but this is now not cryptography, but you saw it in the context of cryptography, take into account that it could be that there is kind of some side information, and this side information is quantum mechanical. This could even be the case if the bit itself is classical. So you could have a quantum memory which carries information about the classical bit, which means, this is just a fancy way of saying there is some quantum state correlated to the classical bit. But you saw in the lecture of Stefanie that this was, for example, the information that an adversary could have about a possible key. So that's how you model it. And now, from a thermodynamic point of view, we now don't think about adversaries. So the side information is maybe the information we have or our device has, so we can exploit it. So we could ask ourselves, is there a mechanism, an erasure mechanism, which erases the bit, so it puts it back to 0, but uses this side information in a clever way. But it shouldn't, of course, destroy it. So maybe one should draw it more like that. So it uses the side information. So again, without I mentioned it now many times. So the machine is also coupled to a thermal bath. But the question is now, does side information about the bit help us in erasing it? And you can, of course, already ask that question classically, because the side information could, of course, as well be classical. So if the bit is not completely unknown, but you know something about it, what is now the amount of work you need to invest to erase it? And what comes out is something very, very interesting, namely that the amount of work required, so the new Landauer formula for this particular case tells you now that it's again kBT, ln2, but there is an additional factor, which is the entropy. And actually it's not the Shannon entropy, but it's, you saw these one-shot entropies of Stephanie, the mean entropy, but I will, there are actually two. There's a mean entropy and a max entropy, which are kind of dual to each other. So in this case, it's the max entropy, but you should think of it in the somehow analogous way as the mean entropy. So it characterizes something you can do in one step, but avoids problems you would have in many steps. And this essentially is X given E. So let's call this E. This is kind of like the side information E to keep the notation that Stephanie had. So this is essentially the result. So what does this tell us? So if X is 1 bit, then the entropy can never be larger than 1. So this tells us in the special case where we have a bit, it could be 1, but actually it's a result that in some way contradicts almost Landauer's principle, because it says that in general the work required to erase the bit could be smaller, because this thing could also be 0. But that's not surprising, because if it's 0, this just means that the side information determines the bit. And we saw that yesterday. Someone asked, what if I know the bit? So if I know the bit, so if the side information is a copy of the bit, then I don't need to erase it. I can just, I know, it's 0, I don't need to do anything, and if it's 1, I just flip it. But flipping a bit is a unitary process and can be done in principle at no work cost. But now, what is the intrinsic quantum feature? So quantum mechanically, it could happen that this entropy, X given E, so maybe you remember how it was defined. It's the entropy of rho XE minus the entropy of E, of rho E. This could actually be strictly smaller than 0. For example, if rho XE is a pure state, this is 0. And so it could still be that this is a mixed state. So in particular, if there is entanglement between this bit, if this is a qubit and there is entanglement between this qubit and the environment, let's assume that they are in a Bell state, then this thing would be -1. So the Landauer principle would essentially give you something trivial. It will tell you the work you require is larger or equal than minus something. Now the funny thing is that it turns out it's...
You wrote log of h, which I think you meant...
Oh, ln2. Yes. So thanks. Yes, this should be ln2. So the funny thing is now that it's actually tight. So there is indeed a process that will erase the bit. You use the side information, but at the same time as erasing the bit, you also get work out because this work cost is negative. So in the specific case where we have here entanglement, so let's assume this is in a joint state, XE, and the joint state is just, let's say, 0, 0 plus 1, 1. So if this is the state, it turns out that the W is minus kBT ln2. So in other words, you have a work gain. And this is only possible quantum mechanically, because classically entropies are always zero or positive. Only quantum mechanically with entanglement we can get negative entropies. So we have in quantum mechanics a very kind of strange phenomenon, namely that the Landauer principle generalizes to something where we could even say sometimes we are so lucky that we know so much about this bit, we not only correlated with it, we are entangled with it, that when we erase it, we get something back. So that's kind of now a real quantum feature. I don't now prove that. I should just say, and this is something that is probably important, that this doesn't allow you to violate the second law of thermodynamics. Does anyone see why this does not allow us to break the second law? Yes?
You still need two qubits to encode the state, so at some point you have to erase 2 qubits.
Aha, yes, in some way.
Spend the energy twice and get one back.
Yes, so in some way, I mean, I would say it differently. I would say in this process, I erased the qubit, but I also destroyed the entanglement at the same time. So I couldn't run it cyclically because I would need a fresh entangled bit. But what this thing tells me is that if someone gave me bits which are entangled with side information, I could again use that to drive a car. So that's essentially the bottom line of the whole thing. Okay, so that was now a second thing. Here, there are again many open research questions. So the question is, can we in practice, so this is still a theory result, and there's a proposal in theory that tells us we can in principle achieve that. The question is again, can we build that experimentally? So can anyone demonstrate experimentally that we can do this process at this minimum work cost? But there is also a more fundamental question behind that, namely the question whether in general, if you have any process in nature that we are interested in, like either a computation or, as I said, something that the brain does, or any other process like photosynthesis and so on, can we analyze that and give the best lower bound? And any such bound here will also always kind of be based on a certain model. So to derive that bound, I have to put up a model or come up with a model that tells me this is the set of allowed operations. And there is no agreement in the community what that is. And it's actually quite even hard to, so I said here work, but there's not even an agreement on what work means on a fully quantum level. So for example, it could happen that I have a process which achieves something in a superposition. So it could happen that this erasure process would that there's a different process that would, for example, be successful with probability 1/2, but not with classical probability, but it would output the superposition between an erased bit and a non-erased bit. And then the question is, what does that mean? How much work does such a mechanism consume? Could it even be that it draws energy from the battery in an entangled way? So when you think about this battery, this n-level system that I had, I could ask myself, what happens if the process doesn't just lower that, but it lowers that in a superposition? So I end up with a battery state which is somehow entangled or in a superposition between two levels. How should I count that? Is this now work or not? What is now the relevant state of the battery to get this classical quantity of work? This question has no answer so far, so it's unclear how we measure work in this fully quantum mechanical regime. So this again is just to say that very fundamental questions, even the very definitions of basic concepts like work, are actually open if you go to the completely quantum mechanical regime. And there are always half classical approximations which are not completely satisfying. Yes?
I also say that the work gain is a kind of minimal work gain, and that if you choose a measure in one way, that you get more work out of it.
Aha, so this is again a lower bound. So this is a lower bound, and what I said after is that there is an explicit mechanism as before which achieves the lower bound. So in some way, the statement is there is a machine that does that, but there cannot be a better machine. So we know, so this is essentially completely answered in this case. Yes. Okay, so with that, I would like to thank you, and I hope I convinced you that there are really many research questions that are fundamental in this area. There are also experimental research questions. And if you're more interested in this quantum thermodynamics, then please have a look at this COST network, this European network that I mentioned. So I should maybe write down the name. So it's called a COST network. on quantum thermodynamics, which is kind of open to all European research groups and which offers conference support if you want to organize a conference or attend one. And it also has schools and so on. So it's kind of, the purpose of this network is to bring people together with an interest in these questions, experimentalists, theorists, mathematical physicists, and so on, and to kind of advance this field, which is a very old field, but which now got new input from quantum information. Okay, thanks a lot for your attention, and then I hope you enjoy.